Howdy, howdy, this is Mr. Potter, and today we're going to go over the 2017 Calculus BC free response questions. So let's go ahead and get started. So for the first question, it says a tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h is given by the function where a of h is measured in square feet. The function a is continuous and discrete, decreases as h increases. Selected values for h, a of h, are given in the table. So the first thing they want us to do is use a left Riemann sum. With three subintervals indicated by the data in the table to approximate the volume of the tank, indicate units of measurements. So what's happening is my height for my first rectangle is going to be given by this 50.3, and the base of my rectangle goes from 0 to 2. So I can say that my volume is approximately equal to 50.3 times 2 minus 0. And then I can add this next rectangle, which will have a height of 14.4 and a base which goes from 2 to 5. So 14.4 times 5 minus 2. And then my next rectangle, my third rectangle, has a height of 6.5, and it's going to go from 5 to 10. So 6.5 times 10 minus 5. And of course, I'm more than welcome to leave my answer like this, or I can use a calculator and get 176.3 cubic feet. And of course, it's important for me to put cubic feet because they're asking me for the units of measure here. So simple Riemann sum. For part B, it says, does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. And keep in mind, we're looking at rectangles that are getting progressively smaller. But the other thing they told us is that this is a decreasing function. And because this is a decreasing function, that means that all of this extra area that we've included here is just that, it's extra. So we can say that our estimate is an overestimate. And our reasoning is because our function a of h is a decreasing function. So that's what we're looking for here. There's our justification. On part C, it says the area in square feet of the horizontal cross-section at height h is modeled by the function f, given by f of h equals this. And it says, based on the model, find the volume of the tank and indicate units of measure. So keep in mind, from our table, we know that we're going from 0 feet to 10 feet. So our volume is going to be the definite integral from 0 to 10 of our function f of h with respect to h. So we're going to go to our calculator real quick. We're going to integrate 50.3 divided by our denominator of e to the 0.2 times h plus h, and I'm going to integrate that with respect to h from 0 to 10. And so when we do that, we get 101.325. And keep in mind, they want us to indicate units of measure. We're integrating area, and we're multiplying it times the height, so this is definitely a volume. So this is going to be our, what were our units again? Cubic feet. So feet cubed. All right. So that's part C. Going on to part D, it says water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at the rate of 0.26 foot per minute. Using the model from part C, find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet, and they want us to indicate units of measure. So what we're looking for here is we're looking for the change in area with respect to time. And because of the chain rule, that's going to be the change in area with respect to height times the change in height with respect to time. Now I know this change in height is this 0.26 foot per minute. And from the previous problem, we know that our area is given by this formula. So what I want to do is I really want to take the derivative of that formula. So I'm going to need to take the derivative of this formula, 50.3 divided by e to the 0.2h plus h. And I want to take that derivative at h equals 5, and I want to multiply that times 0.26. So taking our handy dandy calculator, we're going to take the derivative of my numerator, 50.3, divided by, this is going to be e to the 0.2 times h, close parentheses, plus h, close parentheses. And I want to take this with respect to x. I'm going to close parentheses, at x equals 5. And then whatever I get from that calculation, I'm going to want to multiply by 0.26. And so I end up getting negative 0.338884. So negative 0.339. And again, they're asking us for our units of measure. Keep in mind that this is a change in area with respect to time. So this is going to be square feet per minute. So that's question 1. All right, moving on to question 2, it says, the figure above shows the polar curves r equals f of theta, which is 1 plus sin 2 theta times cosine 2, sin theta times cosine 2 theta, and r equals g of theta equals 2 cosine theta, on the domain 0 to pi over 2. It says, let r be the region in the first quadrant bounded by the curve r equals f of theta and the x-axis. S is going to be the region in the first quadrant bounded by the curve r equals f of theta and the curve r equals g of x and the x-axis. And the first thing they're asking for is to find the area of r. Remember that if I want the area of a polar graph, then what I'm really looking for is the integral from theta 1 to theta 2 of 1/2 r squared d theta. So for us, this is going to be the integral from 0 to pi over 2 of 1/2 times r, which in this case is 1 plus the sine of theta times the cosine of 2 theta squared d theta. So again, going back to our calculator, let's go ahead and clear this up. I want to integrate, and I'm going to integrate 0.5 times the expression 1 plus the sine of theta times the cosine of 2 theta, and I want to take that expression and square it. I'm going to integrate this with respect to theta, and I'm going to do it from 0 to pi divided by 2. So I'm going to do this calculation, and we get 0.648. So our area, or actually I should say r, is going to be equal to that 0.648. And again, the nice thing about this problem is because there are no units given in the diagram or in the text, I have no units here, so it's just 0.648. Moving on to part B, it says the ray theta equals k, where 0 is less than k is less than pi over 2, divides S into 2 regions of equal area, and it says write but do not solve an equation involving one or more integrals, whose solution gives the value of k. So what I essentially want to do is set those integrals that we were talking about from theta 1 to theta 2 and another integral from theta 2 to theta 3 to be equal to each other. So I'm going to be doing the integral from 0 to k of, this is going to be 1/2 f squared theta minus 1/2 g squared theta d theta. That's going to be the area for the first one, because remember they told us S is the area between f of x and g of x. And to be honest, the order doesn't matter here as long as I stay consistent. So the integral from k to pi over 2 of 1/2 f squared theta minus 1/2 g squared theta. Again, the idea here is that because I want the two regions to be of equal area, I want to make sure that they're equal to each other. And because if I take a look back at my diagram, I'm looking for some ray where the area over here equals the area over here. Now, obviously, I've drawn a very poor line as an initial guess, but if this ray, theta equals k, is my dividing line, then I'm going to have the integral from 0 to k of my outer function, this is my big R, minus my inner function, let's call this little r, and then I'm going to be doing from theta equals k to theta equals pi over 2, which gets me through the first quadrant. Moving on to part C, it says, for each theta, 0 less than theta less than pi over 2, let w of theta be the distance between the points with polar coordinates f of theta, comma theta, and g of theta, comma theta. Write an expression for w of theta, then find WA, the average value of W of theta, over this integral. So, real quick, I'm going to make a real quick note from Algebra 1. We know that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So for us, we need to remember that x is equal to r times cosine theta and y equals r minus sine theta. But for us, we have two different definitions of r. We have r where r is determined by f of theta, but we also have r where r is determined by g of theta. So I'm going to say that w of theta is going to be given by the square root of this expression. Keep in mind that x2 is going to be dealing with g and cosine. So this is going to be our 2 cosine theta times cosine theta minus x1 is dealing with f. So this is going to be our 1 plus sine theta cosine 2 theta times cosine theta, and that expression is going to be squared, minus x2 minus x1 quantity squared. Now I need to deal with y for g of theta. That's going to be my y2 plus, this is going to be 2 cosine theta times sine theta minus, and now it's going to be for y1, it's going to be f of theta evaluated at r times sine theta. So it's going to be 1 plus sine theta cosine 2 theta times sine theta, and then this expression is going to be squared. Ugliness, but this simplifies. Now what I have here is technically a correct answer for writing an expression for w of theta, but it's going to be horrible for me to continue the calculation. So I do need to do some simplification. And the thing I notice is that I do have a cosine on each of these terms, which I could factor out as cosine squared theta, because this squared. And then I'm going to have 2 cosine theta minus the expression 1 minus sine theta cosine 2 theta. And that's squared. Plus, keep in mind all of this is under a radical. I could do the same thing here with my sines. I could factor that out, so that would be sine squared theta. And when I do, I end up with 2 cosine theta minus the expression 1 plus sine theta cosine 2 theta quantity squared. And I notice a couple of things here. Number one, I notice that this expression and this expression are the same. And I also notice that I have cosine squared and sine squared, which is 1. So I end up with the square root of an expression that's squared. So this is really equal to the absolute value of 2 cosine theta minus the expression 1 minus sine theta cosine 2 theta. And the square root and the squared end up giving us this absolute value. So here's an expression for w of theta. And going back to our diagram, I notice that my cosine of 2 theta, this outer function, is always greater than or equal to my f of theta, this inner loop, 1 plus sine theta cosine 2 theta. So because of that, I really can get away with not having these absolute value bars here. And of course, that's going to be nice when I'm trying to calculate w of a. So it says find w of a, the average value of w theta, over the interval 0 to pi over 2. Now, recall, and I'm going to do this in a different color just so it's not as confusing, that the average value is the integral, it's 1 over b minus a times the integral from a to b of whatever my function is. My function in this case is w. b is pi over 2, and a is 0. So I really have 1 over pi over 2 times the integral from 0 to pi over 2 of this expression, 2 cosine theta minus the expression 1 minus sine theta cosine 2 theta, all of that being integrated with respect to theta. So we're going to go to our handy dandy calculator. We're going to do 2 divided by pi times the integral, and we're going to integrate our function, which is 2 times the cosine of theta minus the expression 1 plus the sine of theta times the cosine of 2 theta, close for the parentheses, close for the subtraction expression, and I believe that's everything. Let me check. Oh, one more for the function itself. And I'm going to integrate that with respect to my theta variable from 0 to pi over 2. And we end up with this expression, but we can always ask it for a decimal approximation. So w sub a will come out to 0.485. So moving on to part D. Part D says, using the information in part C, find the value of theta for which w of theta equals w of a. And it wants to know, is this function w of theta increasing or decreasing at that value? Give a reason for your answer. So what I've got is that our 2 cosine theta minus the expression 1 plus sine theta cosine 2 theta has got to be equal to 0.485. And I want to solve this for theta somewhere between 0 and pi over 2. So one last time to our calculator. Let's go back over here. We're going to do 2 cosine of theta minus the expression 1 plus sine of theta times the cosine of 2 theta. And I want this to be equal to 0.485. And I want to solve this. So under algebra, I want to solve. And I want to solve this for my variable. And missing parentheses. Probably need to close a parentheses here. And of course, more solutions may exist because we're triggy, but it should give us a good answer. Come on, come on, come on. And by the way, when you're working the AP exam, sometimes you'll have a calculation here and then you'll want to start writing stuff down. Now, keep in mind, I'm looking for an answer that's somewhere in this domain, so I need to make sure that I'm choosing answers that are in that domain. So I've got negative 13, no. Negative 5, no. Negative 0.75, no. 0.5184. That's a first quadrant angle. Let's see, what else do I have? Oh, that's 5.523. That's more than pi. So theta is 0.518. And now I want to know, is the function increasing or decreasing at that value of theta, which really means I want to find the derivative of w with respect to theta at theta equals 0.518. So let's go to the calculator one last time. Now I want to actually take the derivative of 2 cosine theta minus the expression 1 plus sine of theta times the cosine of 2 theta. And I'm going to want to take the derivative of this with respect to x. And I want to know what happens at x equals 0.518. And when I do that, I end up getting negative point, well, it really doesn't matter. What matters to me is, negative 0.581, which is less than 0. So since dw d theta is less than 0, w is decreasing at theta equals 0.518. Alright, so on to question 3. This question 3 says the function is differentiable in the closed interval and satisfies that f of negative 2 equals 7. The graph of f prime is given above, and they want us to find f of negative 6 and f of 5. Now to work this problem, we're going to use the idea that I can say that f of a particular value is going to be equal to the integral from, well, I know that f of negative 2 is 7, so from negative 2 to a of f prime of x dx, plus, since f of negative 2 is 7, I can just add 7 to it. So I'm going to use this to find f of negative 6 and f of 5, and remember that this is the area under the curve, so I can use these areas to help me determine these functions' values. So I'm going to first start with f of negative 6, which is going to be equal to 7 plus the integral from negative 2 to negative 6 of f prime of x dx. And noticing what I've done here is that these appear to be in the wrong order. When we normally think of limits of integration, we usually write them with the lower number on the bottom and the upper level on the top. But remember that I can switch these integrals of this limits of integration by changing the sign in front. So it's really going to be 7 minus whatever the area of this triangle is, this triangle which has a base of 4 and a height of 2. So I can really just put 1/2 times my base times my height. And this is a beautiful answer. I don't have to say 3. I am perfectly fine just leaving my answer like this. Similarly, if I want to evaluate f of 5, I'm just going to take 7 plus the integral from negative 2 to 5 of f prime of x dx. And because I'm going from negative 2 to 5, I'm going from here all the way to here, which means I have a negative area down here, this semicircle, but I also have this positive area, this triangle. So I could say that it's 7 minus the area of that semicircle, which is going to be 1/2 pi times my radius squared, plus the area of this triangle, which has a base of 3, 1/2 of the base of 3 and the height of 2. And again, this is a perfectly fine answer. I don't have to say it's 10 minus 2 pi. I'm perfectly fine with leaving it like this. So moving on to part B, it says, on what intervals is f increasing? Justify your answer. Keep in mind that f is going to increase whenever my derivative is greater than 0. So here f is increasing on the interval from -6 to -2 because this part of my graph lies above the x-axis, and from 2 to 5 because this part of my graph is above the x-axis. So because f prime is greater than 0. So I need to make sure I answer the question and I justify the answer. On part C, it says find the absolute minimum of f on the closed interval -6, 5. Justify your answer. Keep in mind that it's easy to find the relative minimum. It's going to be wherever f prime changes from negative to positive. And that happens at this point here. That's where my derivative was negative and now it's positive. So I have a relative minimum at x equals 2. But keep in mind, because I'm looking for absolute, I have to consider my endpoints. So in other words, I have to look at x equals -6 and x equals 5. Luckily, though, we just found these in part A. So going back to our work in part A, we know that f of -6 is going to be 7 minus the 1/2 times my base times my height. And I know that f of 5 is going to be 7 minus that half circle plus the area of that triangle, 1/2 times my base times my height. Now if I want to find f of 2, keep in mind that it's going to go from -2 to 2, so it is just this semicircle. So it's going to be equal to 7 minus 1/2 pi times r squared. And so I know that this is less than 5 because f of 5 adds this term here. And I can look at this from a basic calculation part. 2 times pi is going to be 6.28. So 7 minus 6.8. This is actually going to be less than 1, where this value here is equal to 3. So f of 2 is an absolute minimum because f of 2 is at a critical point, and it's actually a relative minimum and less than the endpoints. I need to put some type of justification for that there. Usually the math itself is enough. And you'll probably get points for finding the relative minimum, considering the endpoints, and eliminating them. And then finally on part D, it says for each of f double prime of -5 and f double prime of 3, find the value or explain why it doesn't exist. Keep in mind that when I'm talking about f double prime of -5, I'm really talking about f prime of x's derivative at x equals 5. But for us, this is equal to the slope of the line segment. In other words, the slope of this line segment, which goes down 2 and over 4. So this is going to have a slope of -1/2. If I want to find the second derivative at 3, I run into a bigger problem. Notice that at 3 I actually have a corner, so this is undefined because f prime has a corner at x equals 3. So that allows me to deal with that problem. So that's problem 3. Moving on to question 4, it says at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius, with the internal temperature of the potato being greater than 27 for all times t greater than 0. That's going to be very important for us. The internal temperature is given by this differential equation. Notice that this differential equation is in terms of our dependent variable, not our independent variable. This is something we've seen quite a bit of on the AP exam. In part A, they want us to write an equation for the line tangent to the graph of h at t equals 0. Remember that a tangent line can be written in the form y minus y1 equals my slope times x minus x1. And luckily I know what x1 and y1 are. That's going to be the 91. So all I need to do is figure out what this slope is, and I'm good to go. My slope is going to be whatever the derivative is for h, but notice that h is 91. So I end up with negative 1/4 times 91 minus 27. And this is a perfectly legitimate answer, although it would be helpful to know that this comes out to be 64, and so I could really write this as negative 16x plus 91. Now, this is a perfectly valid answer. Of course, getting rid of that 64. This is a perfectly good tangent line. But knowing this little tidbit can make further problems a little bit easier. The calculation's not too difficult, but there's no reason to make that calculation if we don't have to. Part B wants us to find the second derivative of h with respect to t to determine if this is an underestimate or an overestimate at time t equals 3. Wait, did I finish answering that question? I found the tangent line and then used this equation to approximate what happens at t equals 3. So y of 3, in other words, h of 3, is approximately equal to negative 16 times 3 plus 91. And again, I can leave my answer like that, but it might be helpful to know that 16 times 3 is 48, and 91 from 48 is 43. And because they do mention units, it would be really helpful to put our units here, 43 degrees Celsius. All right, moving on, I'm looking for the second derivative. So that's really the derivative with respect to t of dh dt. So I'm looking for the derivative with respect to t of this negative 1/4 h minus 27. But keep in mind, this is not t, this is h. So if I take the derivative of a scalar multiple, that negative 1/4 will stay there. The derivative of h is dh dt minus the derivative of 27, that's a constant. So I really end up with negative 1/4 times dh dt, which is negative 1/4 times h minus 27. Now, I look at this, and I notice that this is always going to be greater than 0 for two reasons. One, this negative times a negative is going to give me a positive. And for two, I know that h is greater than 27, so h minus 27 is greater than 0 for all t greater than 0. So since h is concave up, what I'm looking at is the tangent line approximation that I had for a concave up graph means that my tangent line is going to be an overestimate. So part A is an overestimate. Now, the biggest mistake is that people are going to want to say that this is really negative 1/4 of t minus 27 and just say that the second derivative is negative 1/4. But that causes a lot of problems. One, because you're ignoring the change in h. And two, if it's negative 1/4, this is actually going to be concave down and give us an underestimate, not an overestimate. But because our tangent line lies completely above this curve for all t greater than 0, then this tangent line has to be an overestimate. Finally, moving on to part C. This is our solving a differential equation, the five-step process that we've talked about. Keep in mind, the five-step process, what we're doing, the first thing we want to do is separate our variables. So I've got different variables here. I want to make sure all of my dependent variables are on one side, my independent variables are on the other side. So g is my dependent variable. I want to move this g minus 27 to the 2/3 power over to the left side. And that means all I'm going to have on the right side is a negative 1 dt. So that's my first step. My second step is to integrate this. So, of course, integrating this side is just going to give me negative t. Integrating this side is going to give me, let's see, this is g minus 27 to the negative 2/3. So adding to this is going to give me g minus 27 to the 1/3 divided by 1/3, so really multiplying by 3, equals negative t plus a constant. Remember, step 3 is we have to have that constant of integration. Now what I want to do is solve for g, and then later on I'll use this tidbit of information to actually solve for my constant. So first thing I'm going to do is move the 3 over. So g minus 27 to the 1/3 is equal to negative 1/3 plus a constant. I'm just using a different letter to signify it's a different constant, but it is a constant. Then I'm going to raise each of these to the 3rd power. So this is going to be really k minus 1/3 t over 3, t over 3. Horrible mistake. To the 3rd power. And then I can move this 27 over. So what I've got is I've got g of t is really equal to my constant minus t over 3 cubed plus 27. And now I can use this tidbit here. So I have 91 equals, this is going to be k minus t 0 over 3 cubed plus 27. So 91 equals my constant cubed plus 27. And 91 minus 27, as we saw before, was 64. So for us, k is 4. So our function is g of t equals 4 minus t over 3 cubed plus 27. And then I can just go in here and substitute what happens at t equals 3. So I get 4 minus 1 cubed plus 27, which ends up being 54 degrees Celsius. Now, keep in mind that we were talking about the previous answer that we had being an overestimate, so we've got another one here. So that's problem 4. And on to problem 5. So in problem 5, we're given this function and we want to find the slope. Now, it's going to be real easy for us to think of this as 3 times something to the negative 1 power, this 2x squared minus 7x plus 5. And I want to take the derivative of this to find the slope. My slope is going to be whatever the derivative is at x equals 3. So for us, it's going to be negative 3 times my quantity to the negative 2 power, 2x squared minus 7x plus 5, times the chain rule, 4x minus 7. And I'm evaluating this at x equals 3. So I end up with negative 3 times 4 times 3 minus 7 all over 2 times 3 squared minus 7 times 3 plus 5. And of course, this is a beautiful answer. I don't need to worry about trying to simplify this. It's probably not going to be very helpful for me to simplify this. Moving on, part B. Says find the x-coordinate of each critical point. Remember, critical points are where the second derivative, or excuse me, where the first derivative equals 0 or it's undefined on this interval from 1 to 2.5. They want us to classify each critical point as a relative minimum, relative maximum, or neither, justify our answers. So remember that our derivative is negative 3. Isn't that right? Negative 3? Yeah, negative 3. Negative 3 times 4x minus 7 over 2x squared minus 7x plus 5. And I want to know where this is equal to 0 or where it's undefined, which is where the denominator is equal to 0. So if I have 4x minus 7 equals 0, then x equals 7/4. Over here, if I try and solve this quadratic, I can do this by factoring by grouping. And so I end up with 2x minus 5 times x minus 1. So I end up with x equals 1 or x equals 5/2. Luckily, both of these we don't have to worry about because they're the boundaries of our interval. So what we want to do is we want to understand the behavior of our derivative between, basically around the point 7/4. So I need to test this by taking a look at what happens to my derivative on either side. Keep in mind, I'm sorry, this was supposed to be squared, but that really doesn't matter too much. This is always going to be negative, and this is always going to be positive, which means this expression is really the only thing that determines the sign, the SIGN, of our derivative expression. So if x is less than 7/4, say if x is 1.5, 4 times 1.5 is 6, 6 minus 7 is -1, and because my derivative is less than 0, that means that we are decreasing on the interval from 1 to 7/4. And if I try a value that's larger, like 2, that's 4 times 2, which is 8, minus 7, which is 1. So f prime is greater than 0, which means we're increasing from 7/4 to 2.5. So we have a critical point at x equals 7/4 because f prime changes from decreasing to increasing. Now keep in mind, notice I didn't just put a minus sign here and put a plus sign here and say that's my answer. I actually need to put all of these pieces down. I need to say what I know about the derivative, I need to say increasing or decreasing, and I need to specify the interval on which that's happening. I had to do the same thing for this other interval. I didn't just put a plus and say I'm done. I need to actually show work. I actually need to explain using mathematical terminology, not just pluses or minuses. All right, moving on to C, I've got an improper integral. I've got the integral from 5 to infinity of f of x. Now keep in mind, when I'm doing problems like this, I want to change my infinities to some variable and then look for the limit as that variable increases without bound. So I'm looking for the limit as b increases without bound of the integral from 5 to b of my function 2 over 2x minus 5 minus 1 over x minus 1 dx. So if I'm integrating it, this is a natural log. If I let u be 2x minus 5, then du is going to be 2. And so this comes out to be, again, having to put that limit down. This is going to be the natural log of the absolute value of 2x minus 5 minus the natural log of x minus 1. And I'm evaluating this from x equals 5 to x equals b. Now, this is a natural log difference, so I can combine this into a single natural log. So I'm looking for the natural log, again, limit as b increases without bound, the natural log of 2x minus 5 over x minus 1. And I'm going to do this for x equals b. So as b increases without bound, I've got the natural log of 2b minus 5 over b minus 1 minus the natural log of 2 times 5 minus 5 over 5 minus 1. So, again, remember to close that absolute value. Here, if I take a look at the limit as b approaches infinity, this really becomes the natural log of 2. And this ends up being the natural log of, well, I can leave it as 2 times 5 minus 5 over 5 minus 1. I can leave it like that. I don't have to say natural log of 2 minus the natural log of 5/4, and I don't have to say it's the natural log of 8/5. I've got a numeric answer at this point. It's perfectly reasonable, perfectly valid, and I've evaluated it. It does not diverge. And what's really nice is that this answer is going to help us answer Part D. At least it's one way that we can do it. Part D is asking if this sum 3 over 2n squared minus 7n plus 5 converges or diverges. Keep in mind that because f of x is decreasing, approaching 0, then we can use something called the integral test. So since the integral from 5 to infinity of f of x converges, the sum from n equals 5 to infinity of f of n converges. And if you see that, that's great. If you don't see that, there is another way to approach this. This is the first way that I saw this problem. The first thing I notice is that 3 over 2n squared minus 7n plus 5 is always going to be less than 3 over 2n squared for n greater than or equal to 5. Now the thing is, as long as it's for some point past 5, I'm okay. But this is always going to be true because this denominator will always end up being larger. So, doing this calculation, I can say that the sum of 3 over 2n squared converges, again from n equals 5 to infinity. This is going to converge because of the p-test. And because of that, my original sum, 3 over 2n squared minus 7n plus 5, converges by the comparison test. So that's another way that you can look at it without having to do the integral test. Of course, given part C handed it to you on a silver platter, you might as well use it. And this brings us to part 6. Problem 6 says a function f has derivatives of all orders for -1 less than x less than 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for absolute value of x less than 1. Show that the first non-zero terms of the Maclaurin series are given by this. So let's see. I know that f of 0 is 0, f prime of 0 is 1. If I want f double prime, that means n is 2. So this is -2 times 1, which is -2. If I want to find the third derivative, that means that n is 3, so this is -3 times my previous derivative, which is 6. And I can continue in this idea. The fourth derivative, n is 4, so this is -4 times 6, which is -24. I can keep going with this pattern, but remember that a Maclaurin series is going to be the sum of the nth derivative at 0 times x to the n over n factorial. So for us, the first 4 non-zero terms are going to be, well, there's my first non-zero term. That's going to be 1x to the first over 1 factorial. Here is my second term. That's going to be -2x to the second power over 2 factorial. Here's my next term. It's going to be, did I do that right? I didn't do it right. And this brings us to problem 6. Problem 6 says a function f has derivatives of all orders of magnitude for -1 less than x less than 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for all absolute value of x less than 1. It says show that the first 4 non-zero terms of the Maclaurin series are given by this, and write the general term. So remember, the Maclaurin series is the sum of the nth derivatives at 0 times x to the n over n factorial. So I need to find these derivatives, and luckily they've given us a start. They told us that f of 0 is 0, f prime of 0 is 1. So if I want to find f double prime, that means that n is 1 for my purposes. And so it's going to be -1 times my previous number, which is -1. If I want to find the third derivative, here n is 2, so it's going to be -2 times my previous answer, -1, which is a +2. And if I want to find the fourth derivative, n is 3, so this is going to be -3 times my previous answer, which is negative 6. And so now I'm ready to add the terms. So keep in mind that my function, f of x, is going to be equal to, well, my first 4 non-zero terms, which means I really don't care about that term. So the first term I come up with is going to be this 1, x to the first over 1 factorial, plus I'm going to have negative 1, x squared over 2 factorial. My next term is 2, x cubed over 3 factorial. My next term is negative 6, x to the fourth over 4 factorial. And this is going to continue on. So I really have x to the first minus x squared over 2 plus x cubed over 6 minus x, actually not 6, that's just a 3, because that's 3 factorial, which is 6, divided by 2 is 3. This is minus x to the fourth over 4, plus, and this is going to continue to x to the n over n times negative 1 to the n plus 1. Notice that my even terms are the ones that get the negative signs, and my odd terms are positive, plus dot dot dot. So I need to make sure that I show that I get the first 4 non-zero terms, my work here, and then I need to also show my general term. On B, it says determine whether the Maclaurin series described converges absolutely, conditionally, or diverges at x equals 1. Keep in mind that my series evaluated at 1 is going to be 1 minus a half plus a third minus a fourth plus a fifth minus dot 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 dot. And this is an alternating series test, so this converges. But if I want to look to see if I'm converging absolutely, we converge absolutely if the sum of the absolute value of the terms converges, which doesn't happen because this ends up being the sum of my terms, which is 1 plus a half plus a third plus a fourth. And this is a harmonic series. So this diverges. So the Maclaurin series converges conditionally at x equals 1. So again, I have to do that conditional convergence test the absolute value of the terms to make sure they converge. If they do, great, I converge absolutely, but they don't in this case. So, moving on to part 3. Part 3, they want the first 4 non-zero terms and the general terms of the integration of this. So keep in mind that f of x, as we wrote it, was x minus x squared over 2 factorial plus x cubed over 3 factorial minus x to the fourth over 4 factorial plus stuff. And remember, I had negative 1 to the n plus 1 x to the n over n. So if I want to find g of x, I'm going to have to integrate each of these terms piecewise. So integrating this term gives me x squared over 2. This is going to give us x cubed over 3 times 2. Ooh, horrible, horrible, horrible. It was just 2. It was just 3. It was just 4. Plus x to the fourth over 4 times 3 minus x to the fifth over 5 times 4. And I'm noticing a pattern here. I notice that I still have an alternating series, but my odd terms now carry the negative sign with them. And my denominator is always going to be the product of whatever my exponent is times the number that's 1 less than it. So there's my general term of my Maclaurin series. And now moving on to the last problem. So the last problem says let p of n of 1/2 represent the nth degree Taylor polynomial at x equals 1/2, where g is the function defined in part C. Use the alternating series error bound to show this is true. Remember that from the alternating series, I know that my error is going to be less than the absolute value of what we call the next term. Now for us, because we're talking about a 4th degree polynomial, n is 5. So I want to know what's happening with that 5th term. Now my 5th term, my 5th degree term, keep in mind, is this x to the 5th over 5 times 4. So for us, it's going to be 1/2 to the 5th over 5 times 4. So that's going to be 1 over 2 to the 5th times 1 over 20, essentially. So I have 1 over 32 times 1 over 20, which is 1 over 640, which is definitely less than 1/500th. So I'm using this alternating series test because my series alternates. We saw that from the previous problem. We've seen it twice because of this alternating sign part. And the terms do get smaller and smaller progressively. So we satisfy all the conditions of the alternating series test. We know that G is alternating, and G sub n plus 1 is less than, or I should say A sub n plus 1 is less than A sub n for G equals the sum of A sub n x to the n. So because it satisfies the things we need for the alternating series error bound, we can show this inequality. So once again, these problems were pretty much what we expected, what we saw in the problems that we did in class. Hope you enjoyed the test. Hope you did well. Enjoy your summer. Once again, this is Mr. Potter. Thank you for watching. Have a great day.